So this was the other easy recording, but this is going go backwards. So I was working on this on an earlier stream, or recording, and I worked based on the premise that I could maybe determine two random nodes or two nodes within the tree such that they separated two parts of the tree plus a middle part. I think that ended up just having too many complicated scenarios where trees didn't end up looking like I kind of expected to, and the calculations there were just not. They ended up being too complicated. So, anyways, there's some good ideas, or there were some ideas in there that I'm going to be able to reuse, but I had to restart from scratch in terms of not from scratch. I had to restart in terms of how I want to approach the problem. I am thinking of basically instead of doing two nodes, I just had to. Okay, so for this problem, you're basically eliminate two edges, and you want to find you want to basically calculate the XOR values of the groups that are created, the three groups that are created from two edges being eliminated from the tree. XOR value of a group being the XOR value, each node has a value itself, and you want to take the XOR, exclusive OR, of all the nodes that are connected. So for instance, if you remove these two edges, 11, 4, and 5 are the values of the nodes that are connected here, and you take the XOR of 5, 4, 11 to get the XOR value of this group. The XOR value of this group being one node of value 1 is just going to be 1, this one is just going to be 5. So the overall idea that I had was I just need to, or I wanted to be able to just eliminate two arbitrary edges and quickly determine what the XOR values of the groups are that we generated. Now, if you have, let's say, two edges, let's say there's an edge that is A to B, and there's another edge that is C to D, and A and B, C and D are nodes, two kind of arbitrary edges. Nodes with connecting nodes A to B and C to D. In theory, like one of the nodes could be the same as one of the other nodes, like B could be C or A could be D or something like that. But let's go with that for now. What's going to happen is there's going to be groups formed, and the formation of the groups would be something where there's going to be a middle group, a side group, and another side group, where the middle group will have a connection between one node from the first set with another node from the second set without using the edge that is being selected. So, for instance, if I select these two edges, then technically node 1 is in the same group that is formed from both these two edges being eliminated. They're in this group, and then nodes 0 and 2 are kind of side groups. So there's one group that's in between, and the two groups that are on the side. If I select, let's say, this edge between 1 and 3 and this edge, now let's say I select this edge between 1 and 3 and this edge between 1 and 2, then the middle group would be the one that is sharing node 1. That's this middle group. And then the side group would be the one with 3, 4, and the other side group would be 2. And you can do that with any kind of arbitrary tree structure. Let's say I select this edge and this edge, then there's going to be a side group that is 3, 4, and a side group that's 5, and there's a middle group that is 0, 1, 2. Note here that basically, in order for you one way for you to think about the middle group is the middle group would be on the middle group would share a grouping of the two middle nodes, the two nodes that are not isolated, I guess. Or another way to think about it is for any edge, the two nodes. Okay, for any edge, so let's say the edge is between nodes 3, 1. Any other node that you can think of will be on either the side of 1, so closer to node 1 or connected to node 1 without having to go across this edge, or closer to node 4. So for any edge, I'm going to determine the set of nodes that are connected to the node on one of the nodes of that edge. So I'm going to form, like with this edge, I'm going to say that there's a set that's 3, 4, and another set that's 1, 2, 5, 0. Or for this edge here, there's a set that's just 0, another set that is 4, 3, 1, 2, 5. So for each edge, with nodes A, B, connecting nodes A, B, every other node will be closer or on the side of either node A or B. So this will be, so if I have some dictionary where the edge index is part of tuple and A or B. So for each edge connecting nodes A and B, every other node will be closer or on the side of either A or B. So if I have a dictionary where tuple is the edge index in A or an edge index in B, this is equal a set of closer nodes. So so how does that help? It's going to all right, I think I'm just gonna go through the code. So first thing is I'm going to create the dictionary, which is going to be a graph our graph, which is the default dictionary of sets, and then to form the graph, I'm going to go through every edge that's available. A and B are the nodes, or X and Y are the nodes of that index, and then I'll add onto the set of connections for some node X as the neighboring node and the edge index. And I think, did I ever need to use the edge index? I think I did. When did I ever use the edge index, to be honest? Alright, well, maybe that was not strictly necessary. Maybe I could have just used the edge. Just use the neighbor node. In any case, I create a total variable for calculating the total XOR values of all the nodes in the graph. And then I create a set of leaves, set to store the leaves, and then iterating through all the nodes in the graph. You calculate total by taking the XOR of that node and the current total value. And then you can add to the set of leaves if the current node has no or has one exact neighboring connection. And then moving on from there, there's going to be a few things to keep track of. One is for every node, there's going to be a set of things that are linked to that up to this point in the exploration of the tree, in the exploration of the graph. So I'll keep track of that as a default dictionary, the dictionary being the key being the node, value is the set, and then a set of linked nodes. And I'll also have a default dictionary of the XOR values, which is the key is the node and the value is going to be the XOR of linked nodes as well, up to that point of exploration. And then grouped will be another dictionary. Here this is going to be, the key is a tuple that is the edge index. Yeah, I guess I did need to do the edge index, and then the node, and the value is going to be value grouped will be the set of grouped nodes, and then group XOR is going to be, key is the edge index and the node as well, and the value is going to be the XOR of grouped nodes. And these look similar, but they do differ in the fact of like how much you've explored of the graph. So I'm going to start by creating a double-ended queue of, or just a queue basically, of the leaves, and I'm going to process each node, each leaf node, and during the processing of it, remove the connection between that node and its neighbors, such that some neighbor will eventually become a leaf node themselves because they only have leaf nodes as neighbors. So when those leaf nodes become removed, they only have one other connection that is not a leaf node. So they become a leaf node themselves, and they get added to the queue during that situation. So while there is a node to process, node is going to be popped from left side. There could be a possibility that this node is kind of the last node standing, in which case just break because everything has been processed for it already. But anyways, so thinking about basically processing a leaf node, the node is linked to itself, so it's adding to the list. The node's XOR value is going to be added to, or XORed with the actual value of this node. So if you're starting with 4, or let's say you start with node 0 as a leaf, then the value of that becomes 5. Initially is 0 because it's default dictionary having 0. And then again, this should be at this point a leaf node, so you can pop from the graph of that node its kind of single neighbor, where the single neighbor has the node of it and the edge value or the edge index. Update the neighbor with this node's info, so node XOR of this neighbor. So you're kind of pushing the information. So for instance, if you're processing the leaf node 5 here, so you get the value, this is 2, and then when you process the neighbor, which is this one, you take this 2 and you kind of push that 2 information, that 2 value to this node's value, XOR value. And if there was even stuff like, let's say there was previous other leaf nodes that were connected here, those things would always, that information always is going to be kind of pushed upwards when you do this. And then the linked of the neighbor, so this neighbor here is now going to be linked with everything here and the set of things that are linked here. So it could be just a 5 or it could be other leaf nodes that are on this side of the graph. They're all going to be pushed into the set that is connected right here. And when you push a set onto another set, you use update. So link to the neighbor, update to link to the node, and then update overall information for all the groups. So things that are grouped from this edge. So 5 is the node, edge is this edge. So from this, on this side of the graph, on this side of this edge, with this node is kind of denoting which side of the edge it is, then it's going to be everything that is linked to this 5, so linked to this node 5, and the XOR value of this side is going to be whatever the XOR value of the node is. So grouped XOR is of this edge, and this node is that. And you can quickly calculate the XOR of the other side, which is going to be total excluding the XOR of this side. So total XOR this side is equal to the other side. So group XOR for this edge for the neighbor side is total XOR this side. And then one thing to note here is even though I have group XOR for a particular edge using both nodes on one side and node on the other side, I don't have that for the grouped, the set of things on one side of it, is because, one, I think that's a more costly calculation. So it's easy to calculate the XOR values of total and total minus the group. It's not so easy to calculate the complementary set. So the set that does include the nodes on this side of the set of all nodes that don't include the nodes on this side of the edge. So basically, if it's not here, if a node is not within the set, then it's going to be closer to the neighbor node on that edge. Anyways, after that, you remove the connection to the neighbor. So graph of neighbor, remove from the set of neighbors for it, this node and this edge index. And if the neighbor is now a leaf, put it in the queue. So if the length of the graph of neighbor is 1, explore this double-ended queue is going to append the neighbor. That loops, that's going to process all the nodes up to the point where the last node. And then the second part would be calculating the answer based on those kind of determined XOR values or determined group values. So for every pair of indices, basically this is select any 2 edges to be removed. So index 1, index 2 are the 2 edges. Then you find the nodes that are connected to those edges. And for, let's say, let's say for the first edge, C and D are either going to be closer to A or B. It's going to be like CD is going to be on the same side as A or the same side as B. in terms of grouping. So either A or B will be farther away, or kind of the farthest isolated group from CD. So depending on whether or not you have information for this edge with A set or this edge with B set, if you know for this edge A, then the isolated or the farthest one is going to be B if C is closer to A. So I could also use D as grouped this, but if C is closer to this thing, which means D is also closer to this thing, then B is going to be the farther away. So I can think of B as the isolate group. Otherwise, A is the isolate group. And then vice versa, if I know information about index 1 with B, then if C is closer to B, then A is isolated. Otherwise, B is isolated. And then the mid is going to be the node that's in the middle. And the node that's in the middle is just this is the other node from ISO. So quickly calculating that, you can just do A plus B ISO rather than doing if statement. And then do the same process for the other one. So if you know information about the edge for CD and on the side of C, if A is on that same side, then D is going to be on the farther side. And if you don't know it, but you know the edge for D, if A is closer to D, then C is on the farther side. And then mid is going to be the other node. And then last but not least, the XOR values. The two farthest nodes, the XOR values, just the edge and using the dictionary for group XOR. And the XOR value, the stuff in between, will be excluding the stuff on the side. So so I think I could have just done something like total X. Actually, yeah, this is more complicated than probably I should. I probably should just use something XOR 1, XOR 2. So the total will be excluding the side XOR values. Because when you do XOR values, XOR with itself is 0. So if you eliminate the two side portions of the total XOR, then that should give you the middle XOR. And then find the biggest of the XORs, you find the smallest of the XORs, find the answer as the minimum of the previous answer and the big minus small, and you find that. So again, this is not this ends up being working, but not necessarily optimal. I didn't really come up with whatever the optimal solution would be, but it works. And yes, I will take this ticket. All right. So in summary, this is going to be what is the summary here? I guess the big overall things would be create some graph of the nodes. In this case, the graph maps node to neighbor to list of tuples of neighbor and edge, and then starting with leaf nodes, process nodes in a queue fashion. Track the set of linked nodes and value of an XOR value kind of linked for each node in a dictionary. I guess that's, you probably want to declare that before. I guess in dictionaries rather not in dictionary. Process each node in a queue fashion where you update the linked linked nodes to include linked nodes and XOR value to include this node, and then you push that info to the least single neighbor, prune this node's link to the neighbor, push that neighbor to queue if neighbor is now a leaf, and then post that, iterate over all possible pairs of edges, and then for, let's say those edges were E1, E2, identify what connecting nodes to E1 and E2 are kind of farthest from each other. So those would be, those nodes are the kind of keys to the farthest isolated groups. And then the middle nodes, actually, do I ever need to use the middle nodes? Once I have, yeah, I guess I didn't need mid. Yeah, I guess that was not strictly necessary. Okay, yeah. Get the group XOR for isolated nodes. Those are, and then get the group XOR for middle nodes for isolates for this. So middle nodes, this is going to be total XOR with ISO 1 XORed with ISO 2. And then process that information and update answer appropriately. And then lastly, return the answer. Okay, I mean, yeah, it is what it is. The answer is, or the explanation could be better, could be worse. Could be better. Time complexity, O of n squared to iterate where n is equal to number of edges. Is it n squared? I'm kind of worried that creating the graph and especially getting the sets of nodes that are closest to a particular node on an edge, that might be that's probably n squared still. Like this one statement here where you update the set of things closest to this neighbor to basically copy all the nodes in the current length of this node. That's a very big operation within the grand scheme of things. anyways, to iterate over every pair of nodes, pair of edges to eliminate, and do constant work to update the XOR values to, not, I guess it wouldn't be update, to compare the XOR values. Now that's one part, and then it's, I think, also O of n squared to create the sets of nodes that are closest to every edge and node pair, where edge node 1 or edge node 2, or node 1 and node 2 are connected by that edge. Yeah, it's not particularly efficient currently. So basically this is going to be O of n squared, I think, to create, again, the set of nodes closest to a node for any edge, to one of the edge nodes for any edge in the graph.